welcome to this video. And with this video we will be starting the concept of that is 2 random variable, right? So initially what we were looking is we had a random variable x, right? And we dealt with different values of x, that is small x, and we came across distribution function of x, that is f of x, right? So in many situations we would be interested in simultaneous behavior of two random variables. So if I have x and if I have one more random variable y, and the distribution function earlier was f of y, and each of them we were never concerned about the simultaneous behavior of these two random variables, right? So we were already considered only about their separate statistics, or you can also call it as marginal statistics, that is f of x separately or f of y separately, right? But we were never concerned about the joint statistics of this, right? So we can consider certain examples where we might be actually concerned about the joint behavior. That is, if you have rainfall runoff or rainfall recharge, right? So here we need to consider the uh, the simultaneous behavior, right? So what actually we are concerned here is nothing but if I have a random variable x which takes value x, so x less than x, and intersection with another random variable y less than y is equal, we simply write it as mod x, capital X less than x, comma capital Y, random variable y less than y, and obviously fx of x and fy of y is not sufficient to actually describe their joint statistical behavior. It is not sufficient, right? So we denote hence what we do is we denote x comma y as a 2D random variable, or it's a two-dimensional random variable, right? To understand this, let us take a uh, very famous example, right? So let us consider our very own sample space of tossing two coins. So if I have a sample space given by head head, head tail, tail head, and tail tail, if this is my sample space, let me define a random variable on this, right? So x such that I'm going to get number of heads, right, when a coin is tossed twice, right? So what are my values? So here I have 2 heads, here I have 1 head, whereas here I have 0 head. So this x is going to be nothing but 0, 1 and 2. Similarly, let me consider another random variable y such that I'm going to take number of tails, right? So y is so it's 0, it's 1, and it's 2 here. So it's 0, 1 and 2, right? So these are the values taken by random variable, and it can be x1, x2, x3, and y1, y2, and y3, right? Let us try to do one thing here, right? So let us try to plot whatever we have shown here in a simple xy plane. So if this is my x axis, if this is going to be my y axis, and this is going to be my sample space S, right? Let S1 be a value and S2 be a value. So this mapping of S1 to here, right, to x1, and this is x of S1, and the mapping of S2 here, right, this is x of S2. Also the mapping can be on the y axis, right, the mapping here, that is my y1, this is going to be y of S2, and my mapping here, that is nothing but that's going to be y of S1 and y2 here, right. These are my two mappings here, and if I just drop it here like this, I am going to have x1 and y1 here, and if I just do it here, this is going to be x2 and y2. So these 2 points, that is x1 y1 and x2 y2, are nothing but random points, right. Also it's obvious, but it's very important to know that x takes the value from minus infinity to infinity, also y takes the value from minus infinity to infinity. So this is what it takes, and what we have seen here, that is x and these two, so that is y, these are nothing but these are just two functions, right. These are two functions of the random variable x and y, right. Let us try to understand it more clearly, right. So for this, what we will do is, let us consider two events. So let A and B be two events, right. So if I have my sample space, just ignore my art, and if this sample space is S, and let A be an event and let B be another event, right. So A is nothing but let A is equal to x less than x, right. So we will understand it more clearly by using a graphical notation, by plotting them, right. So B is equal to y less than y. So these are going to be my two events. So what I'll try to do is, let me just plot it here in my xy plane. So this Sj is nothing but this is going to be our joint sample space, right. So if I have to take x less than x, so if I have my value of x here, and if I just do a boundary here, right. So guess what is x less than x going to be? It's going to be here, right. So let me choose a different color to understand this. So let me just draw it like this, right. Just draw it here for your better understanding. This is nothing but my event A, right. So let me define this one more event B, right. So I need to define B, that is y, if this is y less than y, it's going to be something like this, right. Well and good, it's fine till here. So y less than y is what I am trying to show it to here, that is this part, right. So the part here, the intersection here, that is A intersection B, is nothing but this common area, what we are trying to show, A intersection B, right. So A intersection B is this common area what we have trying to show, and that is A intersection B is equal to x less than x intersection y less than y, and we simply write it as, just for a convenience, that is x less than x comma y less than y, and we can also write it as x comma y belongs to this region d1, right. So at this point, what do we know? So we know that, let me just quickly switch to the black color here, that is P of A intersection B is equal to, yeah, P of A comma B, we simply write it as, that is probability of x less than x intersection, right, y less than y, where x and y are the values taken by this random variable x and y, right, is equal to probability of x less than x comma y less than y. So this is nothing but our joint distribution function f of x comma y, and here we are at this point giving the relationship of joint cumulative distribution function. At this point we are giving this definition of joint cumulative distribution function, and we are very well to pause this concept. So we'll be later discussing about the joint cumulative distribution function, that is capital F x of x comma y. So this is y, right? So we'll be discussing the properties of this in the coming video. Thank you.